Hi, everyone, and welcome back to Organic Chemistry on YouTube. Today, we're going to be talking about the ozonolysis reaction. This is a super important reaction that is an example of an oxidative cleavage reaction. This is the way that we're converting an alkene into a carbonyl compound. Carbonyl compounds are compounds that contain carbon-oxygen double bonds, and specifically, the ones that we'll be making today are ketones and aldehydes. This reaction is somewhat complicated from a mechanistic standpoint, and there are several steps. Starting from an alkene, we do a 1,3-dipolar cycloaddition. We make a primary ozonide, and this primary ozonide can be converted to a secondary ozonide through a rearrangement, and then we can rearrange one more time from a secondary ozonide to the formation of the actual carbonyl compounds. Okay, so let's explore the reaction of cis-2-butene plus ozone at minus 78 degrees Celsius, followed by dimethyl sulfide to afford these two products, an aldehyde and a ketone. So the first step is what's known as a 1,3-dipolar cycloaddition. I suggest first drawing out the Lewis structure of ozone and any resonance structures that might be relevant. Go ahead and pause the video if you need to, and then return back once you have that done. Okay, so you should have this as one possible resonance structure of ozone. Now, this can undergo the reaction with the alkene in the first step, and this is a reasonable reaction mechanism. Now, when you create this compound here, this is known as a primary ozonide, and the primary ozonide itself is actually pretty unstable. So what happens in the next step is that it rearranges spontaneously using the lone pair electrons from this oxygen to kick down. It breaks this carbon-carbon bond and forms a carbon-oxygen double bond. And then you break this oxygen-oxygen single bond. And when you do that, you end up with a structure that looks like this. So here you have the formation of the ketone, or of a ketone on the right, okay? And then you have this negatively charged oxygen species on the left. Nucleophilic oxygen, this will attack the carbon of the ketone, okay? And then push the electrons from the carbon-oxygen double bond to attack the electrophilic carbon here of the aldehyde. I'm going to just put a formal charge that was missing there. This is known as a secondary ozonide. And in the final step, the dimethyl sulfide, okay, and in the last step, dimethyl sulfide will attack one of the oxygens here, okay, and make a bond with that oxygen. Subsequently, the electrons in this oxygen-oxygen bond will be used to form the carbon-oxygen double bond. And then this carbon-oxygen single bond that's shown here will migrate here to reform that carbon-oxygen double bond. And finally, the two electrons that are in this carbon-oxygen bond will move up to release that oxygen. Notice that the oxygen that I'm going to redraw, maybe highlight in green, is now going to be attached to the initial dimethyl sulfide. So tracking all these different bonding changes, what's resulted is the addition of an oxygen to dimethyl sulfide, and we've created a ketone, which is this piece right here. And we've created an aldehyde, which it results from this piece right here, okay? So from there, you can make the two products, the ketones, the aldehydes, and the dimethyl sulfide, and the dimethyl sulfoxide. So finally, if you want to ask some questions in office hours, here's some that I suggest. How do steric effects control this reaction? 2, are there some functional groups that accelerate these reactions? And 3, are there any other ways to make ketones and aldehydes other than ozonolysis? That's been Organic Chemistry in 5 minutes or less. Thanks for tuning in.